Looks like the stream is just preparing to send to YouTube. And I'll invite Richard to begin recording at his end.
We're good, Michelle.
Great, and I'm now recording to the cloud and we are streaming as well. So we are good to go.
Great, thanks. Well, good evening and welcome to the final presentation of a 5-part webinar series, Troubled Waters. My name is Richard Witham and I'm the chair of the Greater Sudbury Watershed Alliance. Joining me on screen is Terry Rees, Executive Director of the Federation of Ontario Cottagers Associations, Bree Edwards from the Valley Living with Lake Centre, and Dr. John Small, our speaker for this evening. The Greater Sudbury Watershed Alliance recognizes the ancestral land on which we live and work as the traditional territory of the Ojibwe, Odawa, Potawatomi, Algonquin, and Métis peoples. This territory is covered by the treaties of Robinson-Huron, Manitoulin Island, and Treaty 9, with Wakwemekong remaining unceded. We offer our gratitude to the First Nations for their protection of and teachings about our earth and relations. May we honor these teachings. We're recording all of the webinars and links to the recordings will be posted on the FOCA and GSWA websites. The Greater Sudbury Watershed Alliance acts to protect, promote, and advocate for improvements in water quality and healthy watersheds. Although our focus is on the protection of local watersheds, we also critique municipal and provincial government activities that reduce environmental protection and increase the risk to aquatic environments. In 2010, Laurentian University began a transition to become a research-intensive university with a major focus on northern community health and the environment. As part of that transition, we have witnessed the creation of multiple PhD programs, the construction of the Valley Living with Lake Centre as a research hub, and a medical school that focuses on northern issues. The Laurentian University Academic Plan in 2010 identified clean water now and forever as one of the mission statements for the entire university. The realization of this goal is increasingly threatened by the continuing degradation of Northern Ontario watersheds and the future impacts of climate change. These challenges must be addressed by significant research activities and the training of young, inspired researchers. We should not abandon the dream of clean water now and forever. GSWA is very grateful to have partnered with the Federation of Ontario Cottagers Associations and with the Valley Living with Lake Centre in the presentation of this series. And we're interested in learning where our attendees tonight are from. So Michelle, can you bring up the poll? And I'll ask you to just identify your current location. And if we can leave it up for another 5 seconds, we should be good.
We've got lots of responses coming in. We've got about 200 folks all together with us this evening.
Okay. People are much faster than they have been in the past.
You're getting the hang of it.
All right, so again, more people from Southern Ontario than from North. Oh no, we're tied. I was looking at Greater Sudbury, but we've got 44% from each of those areas, another 9% from Canada, 2% from the US, and 1% from another international location. Thank you very much for giving us that information. Terry, over to you.
Thanks, Richard, and welcome everyone tonight. We're so pleased to have everyone join us once again, and we're sure this is going to be yet another fantastic evening. My name is Terry Rees. I'm the Executive Director of the Federation of Ontario Cottagers Associations, and we're an umbrella association of 500 member groups across the province, and we represent the interests of Ontario's 250,000 or so waterfront property owners on the issues that matter most to the communities where we spend time with our families. More information about our products, services, and information are all available at foca.om.ca, and we do a monthly alert that you can sign up, and we send that out to about 11,000 people every month, and we'd be pleased to share our topical information with you as well. We've had a long-standing support for science and citizen science, specifically through our partnership with the Ministry of Environment, Conservation and Parks, through the Lake Partner Program. And as a waterfront community, we've benefited over the years from a lot of insightful research by academics like our series speakers and others, and much of it using the data from the long-term Lake Partner Program data set. We know you'll enjoy Dr. Smol's considerable experience, and he certainly can elaborate on what long-term data can tell us. His definition of long-term may be different than the context of our 2 decades or so, but it'll be fascinating. We're blessed with an abundance of fresh water in Ontario, and with the commitment of all of us and the knowledge and expertise available through partners like Dr. Small and his colleagues, the many talented students he's worked with over the years and mentored, we'll be able to address these important issues that are facing us in the years ahead. I'm sure you're going to enjoy tonight's speaker. Just a reminder, we look for question and answer. So if you mouse over your screen on Zoom, you'll see the Q&A button, and you can enter your questions at any time. If you're on an iDevice, you may have to tap your screen, but you can enter them in the Q&A section of the screen. That way we can get to most of your questions, or as many as we can, and then we'll wrap up about 8:30. So enjoy tonight's event, and we'll have a great, safe evening.
Okay, I get to tell you a little bit about the Valley Living with Lakes Center. I'm Bree Edwards, and I'm a research scientist with the Ministry of the Environment, Conservation and Parks. And I'm lucky to be stationed at the Valley Living with Lakes Center here in Sudbury. Wish I could spend a little bit more time there, hopefully soon. The Valley Living with Lakes Center is a state-of-the-art research facility that's located on Laurentian University campus and situated on the shores of Ramsey Lake. What's really special about the Lake Center is that it is the home to what's known as the Cooperative Freshwater Ecology Unit. And that's a really unique partnership between government agencies like my group, Ministry of Natural Resources and the Canadian Forest Service, as well as university and academic partners from Laurentian and elsewhere, including Queen's. And John Small, our speaker tonight, has been a long time colleague through that partnership, as well as industry and other stakeholders. So tonight, I'm super excited to be introducing our final lecture in the Troubled Water series, and one of Canadian aquatic science's most accomplished leaders, Dr. John Small. Dr. Small is a distinguished professor at Queen's University, the Canada Research Chair in Environmental Change, and the current president of the Academy of Science with the Royal Society of Canada. Dr. Small and his research lab have a very broad array of expertise in ecology and freshwater science, but are most consistently active in paleolimnology, using the past to understand our present and future, as well as the impacts of environmental change in some of the most vulnerable freshwater environments on the planet. John has made an incredible contribution to producing the next generations of science professionals, having supervised more than 100 successful master's and PhD degrees, almost 30 postdoctoral fellows, and well over 100 undergraduate honors students. John has received dozens of awards in teaching, mentorship, and outreach, including the title of 3M National Teaching Fellow, one of the most prestigious of such merits in Canada, recognizing his advocacy for the importance of university and student research, for promoting success in early career research trajectories, and spreading the philosophy of bringing the joy of discovery into the classroom. John is also outspoken and comfortable with merging the worlds of research and advocacy, and has been vocal about the need for those of us and others in academia to communicate their science widely and engage the public to improve science literacy and collective knowledge. Tonight, Dr. Small will be speaking about the importance and role of universities and importantly student research in facing environmental challenges, and demonstrate those important aspects and roles using his work on climate change from extreme northern latitudes to our own backyards, closing with some thoughts on where we should be focusing our efforts going forward. Without further ado, Dr. John Small.
Thank you very much for that nice introduction. I guess I should share my screen now. Right? And do people see that okay?
It's coming up beautifully.
Okay, if no one screams, I figure things are going. Usually people tell you when it's not working. So, okay, get my pointer going. Well, I'm delighted to be here, and thank you very much for the introduction. I was listening to all the lectures in the series, and I found them all very interesting, and I'm glad to be, in some respects, I'm glad to be the last speaker, because in some ways I look at lakes and ecosystems quite differently from most. I look at long-term environmental change, because I think that's where a lot of the answers lay hidden. So the title of my talk is The Power of the Past and Tracking Lake Ecosystem Change in an Anthropocene World. And I think before I go forward on that, I should probably say what I mean by Anthropocene. the Anthropocene is a term that is not yet official. You hear it, you hear about it in newspaper articles and in a variety of other avenues, but it's still not an official term. As you all know, I think geographers and geologists divide Earth history into different epochs and periods, the Precambrian, the Holocene, and so forth. There is now the move about to name a new geological period called the Anthropocene. And the Anthropocene is going to be defined as the period of human-dominated Earth history. Now, this is a major step forward. It's quite remarkable, but humans now dominate the Earth. Humans have figured out ways to change the chemistry of our atmosphere, to alter all our waterways. We now have more erosion coming from human activities from natural sources. We've learned to, change the chemistry of our atmosphere. All these things we've done, and we are now the dominant force on Earth. So the Anthropocene is going to be this time period where geologists and stratigraphers decide that humans have overtaken the planet. And where they put that date is still some controversy. I'm pretty sure it's going to be about 1945. There's no question that humans have affected ecosystems before 1945. A lot of our work shows that. But I think what's critical is that when humans started dominating Earth processes, it's probably right after about the Second World War. It's sometimes referred to as the Great Acceleration. It's when populations increased, when different chemicals increased, and all sorts of other types of changes have been happening. So anyways, that's even though my title is using an unofficial term, that's where that term comes from. I want to begin, though, by making some statements that I feel very strongly about, and that is that science and other forms of scholarship matter more now than ever before. And this is because we are living in an Anthropocene world. At best, science is being underused by politicians and the public at large. And at worst, science is being misinterpreted, misrepresented, and misused. We are living in a very dangerous time. We are not living in the world where we're using evidence-based policy by and large. And I think it's also a time that science and other forms of scholarship are under attack around the world. I think we've seen some positive changes in general throughout Canada over the last few years, but we just have to look what was happening south of the border not too long ago or in many other parts of the world. We're on a fragile truce with using the truth. And this is something that is critical because we need science, we need research, and we need a highly informed citizenry. And just to look at this a little more closely before I get into some of the examples I'll be using, in general, there are three main sources of scientific research. First, there's industrial research, and that's industrial scientists, scientists working for industries. And there's nothing wrong with that. I don't usually interact that much with industrial science, but these are scientists who work and make products and make patents and so on and so forth. That's an important part of the economy and an important part of innovation. Having said that, industrial scientists rarely have the opportunity, especially in the environmental field, to speak freely about the negative impacts of what might be going on. We also have government research, and government scientists are some of the most dedicated people I know. We often hear negative things about government this and government that, but some of the most dedicated and some of the best scientists I know have gone into government research. Again, this is a critical component of the science pie, if you like. However, as we've seen in this country, and maybe we're seeing in some provinces already, government scientists cannot always speak freely, cannot always do the research that is critical, and so they are somewhat often feathered into what they are doing. The third is academic research, and this is primarily research done by academics in universities and colleges. And I would argue this is a critical component of the research pie. This is typically not restricted in any way. We can, as academics, we're allowed speaking about our research, though I would argue many of us don't speak as much as we should about our research. But it is something that is critical to the running of a democracy. And research is absolutely critical. And university research, I believe, is absolutely critical. Research gives options for society. This is critically important for our future survival. We are going to need all the options we can get with all the environmental problems we are causing. And secondly, research produces an informed citizenry, which is critical for a democracy to run effectively, I believe. And this is what we do in universities. I love universities and colleges. I love universities because they're keepers and interpreters and disseminators of our collective knowledge. I love universities because they're also the place where we create new knowledge. That's called research. And that knowledge that can be used to improve our lives. Universities are also where we change lives. As professors, one of our jobs is to communicate our created knowledge, i.e. the products of our research, to students and also to the public at large. My work as an academic reminds me of how important it is for our society to have a well-informed, articulate, socially active, and thoughtful citizens to meet the challenges ahead. This is part of what we try to do in universities. And if I look at the three pillars of a university, I would say it includes research, which is knowledge creation, which is what you need when you're doing teaching, because what you're doing in teaching is communicating the results of this knowledge creation. And the third pillar is service, which includes service to the university, but in here I would include outreach and outreach to the public at large, to politicians, and to policymakers. This is what we do in universities. This is critically important for a democracy to function effectively. It is critically important for the future of this planet. We need those three pillars to continue in a way that we want to live. So if we think of research as knowledge creation and teaching as knowledge communication, basically teaching is, to a large extent, just the discussion and the analysis of the products of our research. And I think research is important in many other ways in a university besides these obviously practical components that I just put out here. Research also keeps academics and students and the joy of discovery, as I use in some of my titles, basically say if you're excited about research, then you're almost certainly excited about communicating your research. And so you're almost always going to be excited about teaching. And I tend to find some of the best researchers are also the best teachers and often the best communicators and the ones who are doing the best service to the community at large. Basically, enthusiasm is contagious. And I think that's what research in universities does. It keeps university people and university students and the staff and the people outside the university contagious about knowledge, knowledge creation, and knowledge communication. And I've also seen, just as I've seen the enthusiasm brought out by research and teaching, I also think cynicism can be just as contagious as enthusiasm. So I believe this is absolutely critically important for universities. Universities are a central focus of a democracy. We have to keep them well funded, and we have to encourage them to continue with their mandates. And finally, of course, why we have universities for students. And here is a way to remind myself to also acknowledge all the wonderful people I've worked with. I'll talk mainly about the Arctic. These happen to be slides from the Arctic, but it's these young people, and these are slides going back some years. On this slide includes a professor, includes two professors actually, includes a senior analyst at the Department of Fisheries and Oceans, and so on and so forth. This is what we do. We train or we educate the future leaders of this planet. And we have many challenges. And what I'm going to talk about first is climate change. I'm going to talk about climate change throughout my talk, actually, but in three different components. One, tracking climate change, one of the effects of climate change, and then one of the more indirects of climate change that are perhaps more of interest locally, at least, to people like in Sudbury or the Boreal Zone. In a publication in 2010, I referred to climate change as the new threat multiplier. Why do I call it that? Well, virtually and we work on many problems. My lab at Queen's University, the Paleoecological Environmental Assessment and Research Lab, or PEARL, we work on a wide spectrum of environmental problems. There's about 40 people. Brian Cumming is the other professor in the group, but we have about 40 people if you count everyone associated with the lab. We work on all 7 continents on all sorts of environmental problems. But virtually every environmental problem I deal with, climate warming is making it worse. And that's why I've called it the threat multiplier. And we have many, many challenges in environmental research. And as we said in the introduction, I look at long-term timescales. And there's reasons for this. when it comes to environmental or ecological decisions, policy questions, these are the typical questions we want to ask as environmental scientists or policymakers. We often come to an environmental problem like perhaps paramedics come to an accident scene or a detective to a murder scene. Things have already happened. It's too late to see what happened. Just like coming and looking at a body, if you're a homicide detective, you're coming in, we have an algal bloom. What happened? We have dead fish. What happened? Really, what you need to know is how we got to that problem. You want to know, for example, what were pre-disturbance conditions? Sudbury was famous for acid rain. That's a very good example to use here. One of the critical questions we had to deal with in acid rain is what were natural conditions? How do we know lakes acidified? You could go and measure the pH of lakes in Algonquin Park or anywhere, and you could show that, yes, the lakes could be acid. But the argument could be made, and I can tell you, because I was on the front line, as were people on this call, like John Gunn and others, people had said, well, they were always acid. They were naturally acid. How do you show that humans made these lakes acidify? And now we think it's a ridiculous question. It wasn't ridiculous when I started my career in the last 1980, late 1980s or late 1990s. These were the questions people were talking about. The only way you can show lakes acidified, you have to find out what's the pH of the lake in the 1800s before acid rain was an issue. Well, you couldn't do that with pH. First of all, no one was measuring pH. Secondly, Sorensen only invented pH in 1909, so we don't know way knowing. We need to know what were pre-disturbance conditions. You want to know what is the range of natural variability. Climate change is a good example. I mean, I don't think anyone can argue something very strange has happened with climate, but the argument is still being made by some people that this is all just part of some natural cycle. You need long-term data. You want to know, have conditions changed? How much? How fast? When? Why? Each of these has a time or a temporal component associated with it. And that is one of the biggest challenges we have in ecological and environmental research. So what we need is we need the past. This is from the title of my talk, The Power of the Past. I always like this quote: we possess nothing certainly except the past. That's one thing that we know has happened. There's a lot of information out there. But this is also the challenge we have in ecological and environmental research, the problem of timescales. And here I just did this analysis just a little over a year ago, but I went to the International Journal Environmental Monitoring Assessment and asked, how long are most aquatic monitoring programs? And this shows you that, about 2/3 are less than 1 year in duration. Over 90% are less than 3 years in duration. That's not to say 3 years or less is not enough time to answer important questions. Of course it is. 3 years or less is the typical time you'd have funding from a grant. 3 years is the typical amount of time you'd ask a PhD student to do his or her field research. But 3 years or less is often not enough to answer those questions I had in the previous slide. So what we do is we try and push that monitoring window back in time. We can do that in a variety of ways. One, we can look at whatever historical records we have. We may not have temperature readings, but maybe we have something like diaries, or a good example is the Hudson's Bay Company in Canada. Hudson's Bay sent proctors over from Scotland and the Hebrides, and they traded with the indigenous people. They didn't write what the temperature was, but they often wrote long flowing letters or diary entries. The lake froze today, or the river thawed. That gave us some sort of climate information. There's also, especially in Canada and northern regions, indigenous knowledge or traditional knowledge. I'll use one example where we've used that in the Arctic. Indigenous peoples, many of them did not have long records of written records, but they have a strong oral tradition. They've often lived very close to the land, and they know a lot about the environments we're dealing with. Then there's issues of modeling. I won't be talking much about modeling here, but that's again a very popular approach. What I'm going to be talking about here is this last block here, natural archives. All around us on this planet, the planet is monitoring the environment for us. It's monitoring in the trees outside my building here. The trees in the tree rings. It's a record of environmental history, dendrochronology. You can go to Antarctica, into the ice cores that I'm sure you've heard about. Ice slowly accumulates over time. It's a history book going back in time. There's all sorts of natural archives around us. The one I'm going to be focusing on here is sediments at the bottom of the lake. And this is the field of Paleolimnology. That's a very large word for a fairly not too complicated field. Limnology, as you know, is the study of lakes and rivers. Paleolimnology is the study of history of lakes and rivers. It's pretty straightforward. lakes slowly fill with mud. So the lakes around Sudbury are about 12,000 years old. That's when the last big ice age left. One of the legacies is that massive ice age left about 12, 13,000 years ago is all the lakes that were left behind. The ice melted, filled up the lakes, and now we have all these beautiful lakes in these depressions that were caused by the last glaciation. So lakes about 12,000 years ago, they started filling with sediment. Sediment comes in from a variety of different sources. Some is coming from outside the lake, things like soil particles, aerially transported contaminants, pollen grains. A lot of it, I'm a limnologist, I'm usually more interested in what's happening within the lake. Of course, you can't divorce the two. Dead algae, dead invertebrates, chemical precipitates. All this is slowly making a history book at the bottom of the lake. 24 hours a day, 365 days of the year, mud is accumulating at the bottom of the lake. It's like a time machine going back in time. If it went right to the bottom, and in the Sudbury Lake, most of those lakes there would have about 3, maybe 4 meters of sediment. If I went right to the bottom, it'd be 12,000 years ago. Went to the top, it's 2021. We have ways of removing these sediment cores and reconstructing the environmental history. What's in there is not just mud, it's fossils of virtually everything that lived in this lake and all this material coming from outside the lake. Because of that information, knowing what that information means is like a history book going back in time. It's like a library of information. Now, I'm going to be talking mainly about the last 200 years or so of history, the Anthropocene period. So I'm not typically going to be taking 4 or 5 meters of sediment. I'm mainly going to be talking about perhaps the last 50 centimeters of most sediment cores. So for that, we have simpler cores. We have ways to take long cores, but this is a much simpler core. It's called the glue core, the glue gravity core. It was built by John Glue, who died 2 years ago. But he was the research technician in my lab who built a lot of this equipment. And it's fairly straightforward. As you appreciate, lake sediment, especially surface lake sediment, is very wet, very easy to mix up. If you're going to use this as a history book going back 200 years, you don't want to mix that sediment. So you have to take that watery sediment very carefully. And this core goes on, you see this plunger here, it goes down in the up position. We slowly lower that sediment into that very loose mud. It's on this line here. And when we're at the right depth, we send a lead messenger down here. It hits this and it puts this plunge out. It makes like a suction. I use the analogy of if you have a milkshake in front of you. A milkshake is about the same consistency as surface sediment. If you had a straw, if you put the straw into the milkshake and you put your thumb on top of the straw and you pulled it out, you took a core of your milkshake. This is sort of the same thing we're doing here. Once we have the history book, then we have to section it. Remember, it's very wet, so we have to be careful. This is a glue extruder, and here I'm sectioning 1/4 of a centimeter at a time, but 2.5 millimeters at a time. For most lake, that's 2 or 3 years of lake history. Every time I cut another 1/4 centimeter off, I'm going back in history, back in history, back in history. I can go back 12,000 years doing this. Now, it looks like mud. I mean, it is mud, but that mud is full of information. It's full of geochemical information, things like pollutants, things like PCBs, DDT is in the sediment, things like copper, zinc, lead, mercury, copper and nickel from Sudbury. This is some of the things we used in the Sudbury region. So you can track the pollutants that have been going into a lake system. You can also track what's happening in the terrestrial ecosystem by pollen grains. If any of you have hay fever, you know there can be a lot of pollen in the grain. Well, every different plant produces a different type of pollen grain, and there's lots of them, and they're very well preserved in lake sediments. So what we do is we go and we look at pollen grains in the sediment history, and we present 10% of maple and 5% of oak and 30% of pine and 15% of ash. We put that together and we can reconstruct how the forest changed. This can also tell us, for example, when humans came and cut down the forest. We see weeds, we see ragweed, for example. We can see when, for example, agriculture started. We see the agriculture crop. So you can reconstruct the terrestrial vegetation. Now, I'm a limnologist. I'm typically more interested in what's happening in the lake itself. And a whole spectrum, virtually everything that lives in the lake is leaving some sort of fossil. It's either morphological that I can use with a microscope. For example, these are algae, diatoms. This will be a key player in our story here. Diatoms are the most common group of algae in Canada. There's thousands of species. They're extremely abundant. They're something like 1/4 to 1/3 of all the production on the planet comes from diatoms. So since they photosynthesize, about every third or fourth breath of oxygen you take is coming from diatom photosynthesis, another way of looking at it. Animal remains like insect fossils or cladostrid remains, Daphnia and things like that. These are made of chitin, these are made of silica. These are all the various things we look at in my lab. So we can reconstruct what lived in the lake. So we can reconstruct the stressors, we can reconstruct what happened on the terrestrial ecosystem, and by looking at these fossils, we can reconstruct how the biology of the lake has changed. If you know how the biology of the lake has changed, you can reconstruct how lakes have changed over time. And I'll give you some examples in a minute. Now, how do I know? So far, I've just said, this is 2 centimeters, this is 200 years. How do I know that? Well, here's my sediment core. Here's a sediment core I took in 2006. But now you see I've put dates, 1998, 1985, 1946, 1900, 1850. How do I know that? Well, if I'm going back thousands of years, we use radiocarbon or C14 dating. Same thing archaeologists use. That's good for going back thousands of years. For going back the last 200 years, you have to use a different method. The main one we use is called lead-210. I won't get into any details, but lead-210 has a half-life of 22 years. It's a naturally occurring isotope. And it decomposes with a half-life of 22 years. If we measure how much lead-210 is in the core, and so we know its half-life is 22 years, that is how I can put dates around the side of this core. And so to give a Canadian context, that's about 1867, where Canada became a country. There's the last time the Toronto Maple Leafs won the Stanley Cup. You can see a lot of sediment has deposited since then. But this is how we can go back in time and deal with these issues. Now, before I go right to my examples, I also want to make one more case about what we do in universities. I keep hearing, are you an applied scientist? Are you a fundamental or a basic scientist? I've never understood what these differences are. It's as if like you're either a basic or an applied scientist, or you're applied or a basic scientist. Usually it's said in a derogatory way, whichever people are asking about it. In universities, we have both. The argument I would make is you cannot have applied science without the basic science. It's like a pyramid. Applied science is totally based on basic science. And this is what we do in universities. We do a lot of the basic science and we do a lot of the applied science. The main difference between pure and applied science is basically just a matter of time. And I think some of the examples I'll show you is how this happened. When I was hired by Queen's University many years ago, my PhD thesis was at looking at how fossil algae can tell us about reconstructing lakes in Ontario since the Ice Age. What could be more esoteric than that? What could be more basic than that, foundational than that? Then, within a year or so of being hired, acid rain was certainly in the headlines. We figured out a way to reconstruct, using our very esoteric basic methods, to reconstruct lake water acidity and paleo pH. Somehow, within about a week, people considered me a fundamental basic scientist. When a week I says, oh, Dutch John, all he does is applied science. I'm the same guy, same techniques, same microscope, same lab, same students. The main difference between pure and applied science is simply a matter of time. And to give you an example of an applied, I'll start off with one quick slide of an applied, a very simple slide, and then I'll get to what I'm talking about here, is work we did in Sudbury, people like with Bill Keller and John Gunn and others. I'm starting off with a very simplified diagram. One problem with the work we do, it is very hard to show the data because it's on these big graphs, but this is a very simplified graph. Some of you may know this lake, it's Baby Lake. We want to know, has Baby Lake acidified because of the smoke at Sudbury, and did it recover? People saying it's recovering. This is a very simplified diagram, but here's the core we took. Here is the lead-210 date, so we dated the core. We took the core in 1990. That's 1980, so we can actually put the dates on it. These are the 4 dominant fossil chrysophytes. Chrysophytes is a type of alga. And what I have up here is the typical pH these algae like to be in. Without going into any detail, Cyanura ecainulata likes very acidic waters, and these like circumneutral waters. Even if you didn't know anything about diet of the chrysophytes, it would be quite clear that in the 1940s, this lake started acidifying, really acidified up until the 1970s or so. Then with emission reductions, you can see this remarkable recovery. This went from being totally esoteric of me as a grad student trying to figure out what are these scales in the fossil record, realizing they're Christfights, realizing I can match them to species, realizing I can find out they live in different types of environments, and suddenly we had an application. It was work like this and work done at Laurentian University, including people who are on this call, that Canada and the US Air Quality Agreement was signed by Brian Mulroney and the Bush Sr. The 30th anniversary of this signing is next week. That's what basic science in a university can get you. That's what applied science in a university can get you. If we did not have that agreement, we don't even want to start thinking of what state our lakes would be in. But this brings me to, these are some of the many things we do in my lab. I want to switch to our new major problem, a much more complicated problem in many ways, which is climate change. These are just some of the things my lab is doing right now, but let's look at climate change. Climate change, you know the names of these gentlemen, Fahrenheit and Celsius. The reason I put them up there is to put their dates. Even though we think we have pretty good climate data, the simple reality is we only had scales going back to the mid 1700s. And even then, no one was measuring temperature in a systematic way. So we have some challenges with reconstructing climate change on long timescales. We do this work all over the world, but I'm going to take you to the high Arctic. I'm going to start in the high Arctic, go to the subarctic, and end up in the boreal forest. Why we often hear the expression, the Arctic is the miners' canaries of the planet. Just like coal miners used to bring down canaries as early warning systems. They were, when the sulfur gas and so forth, methane was increasing, the canaries would start being agitated. The new miners knew we got a problem, get out before the mine blows up. We refer to the high Arctic and other cold regions like that as the miners' canaries of the planet. Why is that? Well, there's a variety of reasons why the Arctic is the first to show signs of climate change and to the highest degree. The main reason, I think most of you know, is albedo or reflectivity. The Arctic in its normal state is white, ice and snow. It's like a big mirror. It's reflecting back large amounts of the sun's energy. I use the analogy, if I go out on a hot Sudbury day out in a Laurentian parking lot, there's a black car and a white car. I put my hands on both cars. They're both going to be hot, but the black car is going to be hotter. That's because it has low albedo and the white car is like a mirror. It's reflecting. It's high albedo. The Arctic in its normal state is like this, ice and snow. But once you start warming the planet with greenhouse gases, more ice and snow melts, more sea ice melts, going from white ice cover to the dark color of water, going from snow cover and ice cover on land to rocks. As it becomes more and more like the black car, it absorbs more heat, it melts faster, and this is what we refer to as a positive feedback. So to put that on graphs, if we cool the temperature, we increase the snow and ice cover, we increase the albedo, and we decrease temperature. But if we start with greenhouse gases increasing the temperature, then we decrease the snow and ice cover, we decrease the albedo, and we end up increasing. This is a positive feedback. It just, once it starts, it's very hard to stop. So this is why the Arctic or places like the Arctic are so sensitive. The Arctic's also a good place to go because to do this kind of work, it's a relatively clean page. Where you go to someplace like Sudbury, you have industrial activity, you have roads, you have agriculture, you have people, and that can complicate the climate signal. If you're in a distant, not to say the Arctic's totally clean, it isn't, but it's a relatively clean page, so we can see things much easier. What you learn it in the Arctic, you develop the techniques in the Arctic, and then you bring them farther south. Another good reason to work in the Arctic is depending how you define Arctic, but about half of Canada's landmass is Arctic, and 2/3 of our coastline is in the Arctic. So we should be working in the Arctic just because it's such an important place for us. Another good reason for a limnologist to go to the Arctic is lakes and ponds dominate the landscape. And every time I see a lake or a pond, I see a place that is a history book where I can actually start doing this. Each of these sites has a history book, as far as I'm concerned, at the bottom of their sediments. So I'm going to start off by going to some of the most sensitive regions in the world in the high Arctic. And I'm going to go up here, it's where I did my earliest work, where I started this work as a young man, 1983. I've been going to the Arctic for, well, I guess approaching 40 years. Hard to believe, but I started very young. I want to point that out. And It's a big country we live in. Getting to the Arctic now is much easier than it was when I started. Now you can take a flight out of Ottawa. There's a flight every day going to Iqaluit, the capital of Nunavut. That you go on a 737 or something like that. It takes about 3 hours or so. You're in Nunavut. Then you heal your, you sit there for a little while. And then you go on a much smaller plane, and you get as far as Resolute Bay. That's Canada's last commercial airport. That's a flight of about another about 5 hours. Then once you're in Resolute Bay, you go on a much smaller plane. I'll show you that in a minute. You fly to something like the sea ice off of Ellesmere Island. Then you go by helicopter, and then you walk. So what I'm getting at is when you're going to a place like this, the sensitive region, it's very difficult to get to, and logistics drives everything. But it is a very interesting place. So once you're in Resolute Bay, this is how you get up to Ellesmere Island. It's called the Twin Otter. Many of you are familiar with it. But I show this photograph. This is in July or June. You still see snow in the background. There's always snow. And we're still going to fly another 3 or 4 hours north. The plane is going to take off on wheels. I don't know how well you see this, but it also has skis. It has wheels and skis. It's going to take off on wheels, but it's going to land on skis because that's how far north we're going. And I should also say, once you're there, you have to move it with a helicopter. So it gives you some idea of how complicated this is. This is what a typical tent camp would look like. Then the helicopter leaves you. You're there for about 3 or 4 weeks. And then you really hope that you brought everything you needed because no one's coming back for several weeks. And so you better have everything. So here's where I started my work. It's called Cape Herschel. It's about, as I show you on that early diagram, it's way up on Ellesmere Island. And that's Greenland in the background. It's about 45 kilometers away. You can almost see the Greenland ice cap on top. And this is what Cape Herschel was, full of lakes and ponds. And this was an ideal place to work on. Now, we hear a lot about Arctic and we hear a lot about sea ice, and we should hear a lot about sea ice because it's very important. I just want to point out that sea ice is very important, but so is lake ice. And going back, again, starting very fundamentally, very basic science, part of my graduate work, I started seeing that one of the biggest things that drove what lived in the lake was how much ice was on the lake. Here's the same lake under a cold conditions, a medium condition, and a warm condition. It's the same lake. Now we're high up. We're about 80 degrees north latitude. So the summer is only a few weeks long. Mind you, it's 24 hours daylight. And what I would see is that if you were in the cold conditions, only because diatoms or algae are photosynthetic and need light, only really the very shallow water organisms would thrive. As the lake got warmer, deep organisms that live in deeper and deeper water could thrive until it got so warm that even what we call planktonic organisms or organisms in the middle of the lake would be thriving. This was very fundamental work when I was doing it in the early 1980s as a graduate student. Climate change wasn't really on the radar screen yet. And this was just an interesting aspect of fundamental science, which I thought was important to understand how lakes function, as we know that. Basically, this is what it was. If it's cold, if you're in a very cold lake, you only had these very small generalist taxa, like these small Fragillaria species. They look like this. If you were in a warmer lake, the summer was longer. You could get far more complex assemblages. You get mosses growing, so on and so forth. You get much more different assemblage. Well, that was basically a paleothermometer or a paleo ice meter. And that again went from being purely fundamental sort of academic university research to applied. And that came with this publication in Science, which is one of the dominant journals we have, with Marianne Douglas, who was a graduate student then, and Wes Blake, who just recently died. We published that in 1994, so over 25 years ago. And basically, this is what we showed. Again, I know these profiles are terrible to look at, right? This is a highly simplified profile from Cape Herschel. This is a cold water species. These are warm water species. These need open ice conditions. These thrive under full ice conditions. So we're going from almost a monoculture of these cold water taxa to this very diverse that needs open water conditions. That's what we published in Science in 1994. We said that in 1994, in this paper in Science, that climate warming has already been happening in these highly sensitive regions, human-induced climate warming. You publish a paper in Science, you feel pretty good because it's the major journal, you feel. And we felt pretty good for about a week or so. Pretty quickly, we realized no one actually believed us, except it seems like the journal reviewers and the editor. Remember, now we talk about post-1850 warming as standard. In 1994, that was not the view. First of all, greenhouse gas warming was still kind of sort of in the future. And certainly it wasn't happening already. We were saying it already was happening. We did a lot more other studies. Sure enough, as you got farther south, you showed the same type of changes, but it happened later. This is around Hudson's Bay. We thought we were making clear sense that the diatoms were tracking already clear indications of climate warming. Well, it was in 2005. It was 10 years after the Science paper. I was in Finland at a meeting, and I got together with Alex Wolf, 26 different scientists. And most of these scientists actually didn't believe some of their early work. And that's what you do in science. You don't believe anyone. You don't take anyone's word for it, is the motto of the Royal Society of London. We got them all together, scientists working from all around the world in the Arctic. And as I say, I sometimes think I want to write a paper about writing a paper with 26 authors. But anyways, it ended up being a very nice paper, I think, and published in a high-profile journal. And we showed these same types of changes happening in the circumpolar regions. Lakes were changing. The timing of changes was exactly what you would predict. And it was happening, and it was happening fast. It's already happening. Well, okay. Just to talk a little, just to conclude the Cape Herschel story, I'm going to fast forward from the early 1990s to the last 10 years. We had a lot of data by now in our main high Arctics. We could show from our paleo data, I only showed you one profile. We have many, many profiles, by the way, but they're not easy to look at. We show there were permanent water bodies for thousands of years. We also show they started to change markedly over the last century or so, consistent with climate warming. What's happened with these ponds in the last decade or so, the warmest decade on record? And this is where you see what we refer to as the final ecological threshold. I'm going to show you some photographs here. This is even before I was there. Wes Blake was looking at the glaciers here. He happened to snap a picture of one of my study ponds. But this is what one of our study ponds looked like in July in 1979. Nice, healthy pond. This is not a big pond. This is probably about the size of 2 houses, let's say, or one big house. But that's a typical size of pond in this part of the world. Nice, healthy pond in July. Here, there's a younger John Small, 1987. It's already, the winter snow has come back. It's August. By the end of August, the winter usually comes back. Still a nice, healthy pond. What happens now? This is what the pond looks like by mid-July. It's evaporated away. We know from the paleo data, we can show with these belief from the paleo data, it's been a permanent water body for thousands of years. Now, by July, with the warming, it's evaporated. Here, I'll do a close-up. Here is the last few hours of Camp Pond. You see that puddle there? It's about the size of my desk. That's 2 o'clock in the morning. I went out and I said, ponds we've been studying for many years is about to evaporate on us. It's disappearing. I went and put a piece of white paper in my hand, and that's all the invertebrates, all the animals and algae that lived in a pond were now concentrated in this little puddle. At about 2 o'clock in the morning, it dried up. That's a small pond. Here's Cape Herschel Lagoon, another name. This is about the size of a football field. That's what it looked like in August of 1987. This is what it looks like by mid-July. Even in my lifetime, just since the 1980s, we've gone from being nice, healthy ponds to increasing temperatures, which were decreasing the ice cover. We've taken the lid off the pond. Once you take the lid off the pond and you had warmer temperatures, you're evaporating stuff away, increasing evaporation, decreasing water levels. And because we're increasing evaporation, we're increasing salinity. And why is that? Well, that's because if you let evaporation happen, the water evaporates, but the salts stay behind. And I use the analogy, if you put a pot of soup on the stove on low heat, you take the lid off, that's kind of like these high Arctic ponds in the warmer summers. If you keep watching your soup, the water level keeps going down. That's exactly what we saw happening over the years. The pond levels were going down, down, down. If you keep tasting your soup, it's getting saltier and saltier. That's because the water of the soup is evaporating and it's leaving the salts behind. This is exactly what's been happening in the ponds. And again, another example of how what might be referred to as esoteric, basic research. Since 1983, Marianne Douglas and I have been measuring the salinity of all 38 ponds on a regular basis. it's monitoring. People say, oh, monitoring's not really science. Well, because suddenly, apparently it becomes science when suddenly people realize the value of monitoring. Again, another high profile publication in Peanuts. We had monitoring data of, I have 38 ponds. I only had about 20 left because about 20 of them had evaporated to dryness. So I couldn't measure them anymore. But if I look at what connectivity is, like think of it as salinity, this is salinity of my remaining 20 or so ponds since the 1980s. And the salinity 20 years later. And if it hits the 1-to-1 line, it means the salinity has not changed over the last 20 years. But as you can see, every single site has increased in salinity since the 1980s, except one pond, Pond 32. Pond 32 is exactly the pond we predicted should not increase in salinity. Pond 32 is fed by two streams coming from the two plateaus on the Cape. So it's constantly replenishing it with fresh water. So as predicted, Pond 32 did not change. All the other ponds did. The smallest ponds salinated the most. The larger ponds like Ellison Lake did the least. But again, it's clear that we had that. And again, even though average precipitation has been increasing, we've seen that. Even worse, perhaps, are the wetlands. This is what the wetlands looked like in the 1980s. We even gave them numbers. Right now, the wetlands are so dry that you can actually light them and they catch fire. Of course, this has important implications for carbon storage, carbon sinks. Again, this is just showing how fast this ecosystem is changing. Okay, so I'm going to quickly go to a second and then a final example to finish the talk. This is talking about too little water. I'm going to go from too little fresh water to too much salt water. Another aspect of climate warming, referred to as coastal flooding. And we hear about hurricanes, we hear about ocean inundations. We tend to hear about it in the South, places like Miami, sometimes even New York in some cases. It's making headlines around the world. We don't think about it happening in the Arctic. I'm going to give you an example of it happening in the Arctic. So last time we were way up here in the high Arctic. Now I'm going to go to the subarctic, mid-Arctic, down here in sort of the Mackenzie Delta region in the Western Arctic. And many of you know the Mackenzie River and the Delta. It's the second largest Arctic delta after the Lena Delta in Russia, where we've also done quite a bit of work. But something remarkable happened in 1999. In 1999, there was a massive weather change. In 24th of September, winds from the northwest up to 76 kilometers an hour produced a storm surge in the Delta. So we had these very strong winds, followed behind by a massive storm surge. And that storm surge lasted 48 hours. And because the elevation is so low in the Mackenzie Delta, that was about 2 meters of water, so taller than I think any of us who are listening to this, or probably anyone is listening to it, moved in 20 or 30 kilometers. That's remarkable. It flooded that area going in 20 or 30 kilometers, as I showed here. That was salt water over a freshwater system. Not surprisingly, it killed everything in its wake. Thankfully, no human was killed. They could have been killed because this is the traditional hunting ground of the local peoples, but no one was killed. But here you can see what we call the dead zone. You can actually see the exact line, how far the salt water went. In the distance, you see the Arctic Ocean. Everything here is solidified, salinated because of it happened in 1999, it's still salty. And you can see the exact line, how far the salt water went. These lakes have higher salinity. These lakes are fresh. This land is still quite fresh. All the plant and animal life here has died because of the salt water. So we asked a question. It happened in 1999 when we came there. How common are these storm surges? Are they really unprecedented and possibly linked to climate change? We don't tend to think of the Arctic as being part of this. Well, the first thing, when you go and talk to the local people, and this was actually published in a paper led by Steve Coquelle, but the Inuvialuit people who live there know the area, and this was part of a traditional knowledge thing. And based on traditional knowledge, it has never happened in their oral history. That it was unprecedented 1999 thing. So that was interesting. That made us think we have a long record. Now, of course, even that doesn't go back thousands and thousands of years. So the next step was to look at lake sediment records. There are lakes all through this region. And we reasoned that if we core the lakes, this is mainly the work of Mike Pisaric and Josh Champon. Josh Champon is a former student, who was one of the leads. We went and we took sediment cores from these lakes, And we reasoned that since many of our indicators are very good indicators of salt, we have a paleo salt meter in the fossil record. And we have many indicators. We're going to talk about diatoms, but one of the best indicators of salt are these algae. Again, the diatoms, the same ones I talked about from Cape Herschel. Some diatoms live only in fresh water. Some live in brackish water. Some live only in salt water. And there's thousands of species, and we know very well where they live. So if you look at the percentages of different species, you sort of have a salt meter. And that's what we did. We took sediment cores. The first core we did went back 300 years. We dated it with lead-210. And as you can see, that's the line for lead-210 here for 19. That's when the storm happened. And I think you'd agree the red diatoms are salt diatoms. The blue ones are fresh diatoms. And I think you'd agree that there's a massive change in diatoms right at 1999. There's always been a few salt diatoms. You would expect that with sea spray and so on and so forth. But at least in the last 300 years, this is an unprecedented record. That's exactly what the traditional knowledge told us. It was unprecedented in their traditional history. Okay, being paleoecologists, we took a short core. We said, good, well, that's interesting. Let's see how long we can get. So then we went and took a long core. We went right to the bottom. The lake we were working on, just over 1,000 years old, maybe 1,200 years old. And as you can see, again, that's freshwater diatoms, salt diatoms. That's 1999. Once again, the only time we had any appreciable number of salt diatoms is post-1999, after that storm surge. So it appears that, in fact, so we've done like an environmental assessment going back in time. The impact was unprecedented, at least since those lakes were there. They're only a little over 1,000-year-old lakes. It was unprecedented. We did this on one lake. Then we did it on a bunch of lakes. You can do this on a landscape scale. There's lots of lakes. Each dot here is a lake. That's the dead zone. That's how far the ocean water went. And just quickly, every lake we did, exact same story. Post 1999, every lake, it only happened after 1990. It's unprecedented. We go outside the dead zone here as a control, no salt diatoms. It's a straight line. It was unprecedented. So why was the 1990 storm surge unprecedented? Well, the usual culprits, rising sea levels. If sea level rises, it's much more likely to go inland. We know that from happening everywhere. With climate warming, we're getting rising sea levels, happening for two reasons. One, land-based ice in the Arctic is melting, so that land-based ice is raising the sea level. Also, simply the warming of the ocean, it's expanding, so it's raising sea levels. As we all know, there's change in storm frequency and intensity. With climate warming, we're getting more intense weather, bigger storms, like the 1999 storm. But what's quite peculiar for the Arctic, not so much for, if it happens in Puerto Rico or a place like that, later freezing and decreased ice cover. We know the ice cover is decreasing, and this was also a key part of the story. If you go back just to 1979, if you go back to 1979, you can see there was much more extensive ice than there has been more recently. If you have, no matter how much wind you have, if ice is on the ocean, it's not going to make a storm surge. It's a bit like if you have a big fan on your swimming pool making big waves, but you put a cover over the swimming pool, you're not going to make waves. You can have a hurricane wind, but if the ice is there, you're not going to move liquid water. The point being now, with less ice cover, before, when you did have maybe strong winds at this time in September, the ice cover was back. Now it's not. So we actually now have made it completely susceptible to these types of storm surges. Well, is that our new normal? The data showed the 1999 storm surge was unprecedented in at least the last 1,000 years. We did that work about 10 years ago. It happened again in 2016. So what was a once in 1,000-year storm is now twice in 20 years. This is what's happening around the world. You can look at the number of disasters in Canada, climate-related disasters. Look at many of these are water-related, as I'm sure you know, serious issue. Canada is a very industrialized, rich nation. Probably we'll be more or less ready to deal with a lot of these things. Of course, there's an issue of social justice. A lot of these problems are going to happen in tropical island nations where the people haven't really caused the problem, but they're going to be on the front line of the problem. Finally, I'm just going to conclude with a short example, bringing it close to home, and ask, Okay, so what? You show this in the Arctic, you show it in the subarctic. What about places like Ontario? And I'm going to come to something that's a very local nature. And I'm going to talk about algal and cyanobacterial, or algal and blue-green. Cyanobacteria is another name for blue-green algal blooms. Often in the literature, it's referred, in the popular press, talk about blue-green algae. I know they're happening in Sudbury, they're happening in the boreal forest, they're happening all over southern Ontario, and it's become a big concern. What's going on? It's become a big concern because we thought we understood this. We said you add nutrients, you get an algal bloom. No question that's correct. No question that increasing phosphorus levels is going to cause higher algae. You get with higher algae, you get shoreline fouling, toxins. Some of these are dangerous, taste and odor problems, property values drop, deep water fish die, aesthetic degradation. No one wants to go swimming in a algae infested pool. And no question, nutrients are important. No question. No question you need. I'm not saying I give a talk once and I didn't have the slide. People says, well, now John Small says nutrients aren't important. Okay, start off by saying they're obviously important. You're not going to get an algal bloom without a certain amount of nutrients. But, and it's a big but, people are, as also in your area of the country, people are recording increased algal blooms, even in lakes with steady or declining nutrient levels. What's going on? Something is changing. And we've been asking the questions as of others. Can climate change be affecting algal blooms, even without increases in nutrients? And what I'm talking about here is what I refer to as the longer summer. Just like I showed in the Arctic, the effects of different ice covers. This is happening. We know it's happening in southern Ontario. Summer's getting weeks longer without ice. That longer summer, we believe, is pushing lakes towards more algal blooms, and especially towards more blue-green algal blooms. And that's because of less ice cover and stronger thermal stratification. I'll give you one example from Lake of the Woods. I'm going now to southern Ontario. I think many of you know Lake of the Woods. It's almost a Great Lake, not quite. It's a very large lake, 2 provinces in 1 state. There's very good data, and they're very proud, as they should be, of how they've cut down phosphorus. Phosphorus load has decreased remarkably into Lake of the Woods. And yet, what's happening? Phosphorus is down. People are seeing algal blooms. What is happening? There seems to be a disconnect. We're having algal, at least people are saying algal, we have to watch about perception because people might forget what things were like 30, 40 years ago. But the public's perception is algal blooms are increasing, yet nutrients have declined remarkably. Can climate change be pushing this towards more algal blooms? Well, these lakes are changing and changing fast because of climate change. I'll give you one example here. Again, this is a highly simplified diagram of only 2 fossils. But basically, Cyclotella is a species that likes warm, open water, stratified, no ice conditions. Olacosyra likes cold, mixing water. You can see that something remarkable happened about 1980 in this bay of Lake of the Woods. And we almost have like here a paleothermometer or paleo ice cover, paleostratification. Look at this. This is Cyclotella, the warm water species. This is actual temperature from meteorological data. You can see how closely our warm water species is matching the known temperature data. Total opposite happening with the cold water Olacosyra. You can see it even better with ice cover. And I think ice cover is the key. As we have ice cover data going back about 50 years. As ice cover goes down, up goes Cyclotella. Or as ice cover goes down, so does the ice cover loving Olacosyra. So we are seeing a tremendous change, we would argue a regime shift change in the ecology of this lake. That seems to coincide with algal blooms increasing. We can actually track past algal blooms, fossil pigments. I'll show you this here. Here's just 3 parts, 3 different bays. And these are not highly productive waters. 14, this is still fairly low phosphorus, 12 and 10. Even at 14, you can see since the 1980s, this is fossil chlorophyll A, so it's showing how much algal production. Still quite a striking change. Even at 12, we see it. Once you get into the very low nutrients, it's far harder to see the change. So it's much less happening. You still need a threshold of nutrients. But what's key is that even though nutrients are fairly low, we are seeing this increase. And what we think is happening is we're going from this relatively cold, well-mixed system to this stratified or less ice system, and that's exacerbating algal blooms, even without further increases in nutrients. And on top of that, not only are the algae increasing, the blue-green algae especially like it hot. And so we've really pushed these coefficients to that part of the world. And, this is Jenny Winter data going back. Algal blooms, the people are showing increasing algal blooms all over Ontario. And we are even showing them, this is work Liz Fafat, just show you 2 slides here. Liz Fafat did this as part of her PhD thesis. She went into Algonquin Park, Dixon Lake. It's in the middle of Algonquin Park. You've got to hike to it. It's clearly not getting sewage. And they had to close the lake to hikers because it had this massive bloom. It started getting these massive blooms. We went and did the paleo study. To make a long story short, sure enough, with warming, we are seeing, it's not saying it's a completely clear story, but these are the fossil blue-greens and the inferred chlorophyll A. Sure enough, it does appear that we're seeing unprecedented levels of primary production and cyanobacteria, blue-green algae, coming with warming. So even these isolated lakes are starting to show it. So just to conclude, basically with climate warming, we're loading the dice for frequency of disasters. I'm not saying each of these was caused by climate change, but with climate warming, it's much more common. You would have had storm surges sometimes in the past, but it's much more likely with climate warming. Another analogy is you playing Russian roulette. Before you had 1 bullet in the revolver, now you have 2. You put a lot more greenhouse gases in the atmosphere, now you have 3. And time is not on our side. I always love this quote by Martin Luther King Jr. It's referred to the fierce urgency of now. He wrote, in this time he was writing about the Vietnam War. From my history, I understand he used this quote twice, the fierce urgency of now. It was with the Vietnam War in 1967 and with civil rights in 1968. But we can say this equally for the environment. In this unfolding conundrum of life and history, there is such a thing as being too late. And what I find frustrating, just coming to my last slides here, I keep hearing, well, why can't the scientists get consensus? And there has been scientific consensus on climate change for years, many years, and time is running out. I'll give you one example of how clear this consensus is. What is very frustrating for me, a recent poll by CBC showed about 1/3 of Canadians weren't convinced climate warming serious climate warming was linked to human activities. It's hard to believe we could have such a disconnect between the scientific evidence, which has been here for a long time, and still public perception. I always like quoting Dr. James Powell. I put this here, there's a lot of detail here, but Dr. Powell is not sort of like a tree-hugging environmentalist. I think his records are, not that I have anything wrong with being a tree-hugging environmentalist. I want to point out, he's been presidents of many universities, of museums. I want to point out President Reagan and later President Bush Sr., both Republican presidents, had enough confidence in him to point him to the National Science Board, where he served for 12 years. He clearly has the credentials, the scientific credentials and the political credentials not to be on a political side, if you like. And what Dr. Powell does is he looks at here's the key, peer-reviewed scientific literature. He looks at the peer-reviewed scientific literature on anthropogenic warming. And he has gone through, looked at over 54,000 journal publications. And he has shown that it's over a 99% acceptance that based on data, peer-reviewed data, human-linked climate warming has been happening. So the ratio in the peer-reviewed scientific literature is 1,747 to 1. Now I ask people, is that not convincing? And I ask, if your daughter or son or mother were sick and you went to 1,748 medical doctors, and of those 1,748 doctors, 1,747 said your child needed help, and 1 said your child was fine, who would you listen to? I think you'd probably listen to the 1,747 doctors. But we live in a world where there was a time not too long ago where someone spent 30 years studying a problem. They were called an expert. But now someone spends 30 or 40 years studying a problem. In some circles, at least, they're called an elite. There was a time when people studied an environmental issue and we got what was called environmental legislation. Now, at least in some quarters, the new term for environmental legislation is red tape. There was some time where people did environmental assessments to find out what's the best way for society in general. Now we talk about not needing environmental assessments. It's under the guise of increasing efficiencies. And we also live in a world, which I just showed in that last example, where you can spend 30 years publishing in Nature, climate change, whatever, and then you're put up next to a basement blogger who has no background, but it's, you're on the media and suddenly it's a debate. I'm on some radio station or television station, and now we have so-and-so who has an opposing view, and I don't even know who this person is. I try and look them up. They run a blog or something. There was a time when expertise, we have to bring that back, and the universities is where that comes from. And we have to show as academics that universities are important and that we can do that. And the way to do that is reaching out to the community and policymakers and show why what we do in universities is important. And we have to show that, what I always love this quote by Daniel Moynihan, senator now deceased, but we can't deal in a world of alternate facts, wishful thinking. Everyone is entitled to his own opinion, but not to his own facts. Opinions don't mean very much in science. Data matters in science. Reproducible data matters. Opinions, you can have lots of those, but in science, you need to have reproducible data. And I hope you see from what that the past matters. I think most of you probably think of monitoring as years or seasons or days, but there's a lot of information here in the sediments, and that's where a lot of the answers lay hidden. I'd just like to end by thanking all the funders, the Canada Research Chairs, the various universities, a large number of students and colleagues, and thank you very much for your attention.
Thank you, John. What a fabulous talk. You covered a lot of ground, and I know there's going to be a wide range of different types of questions. Feel free to grab a drink of water if you need it, take a quick break. I just want to remind everybody that there is the like function on the questions. So if you haven't entered a question, but you see something that resonates with you, it might help me prioritize a little bit in the about 15 minutes that we have for questions. So I'm going to give 1 or 2 more seconds for a little upvoting, and then I will see what pops up to the top of the list. Okay. I think you did a great job of speaking to this in the latter part of your talk, but I think folks would still like to hear a little bit more about how we can push the peer-reviewed science and legitimate science against alternate facts and really have it resonating more with folks that are needed to make those policy changes.
Yes, thank you. I think we're in a bit fighting a bit of an uphill battle, but we can do a lot more. There was a time when we had we still have serious science journalism in this country, but the number of journalisms, of course, is in jeopardy. A lot of people got their scientific information from scientific journalists. There's still some excellent scientific journalists in this country, but it's been dropping and dropping quickly. And we've let the media get away with it. So, I mean, I have examples like this all the time. Like a major climate report comes out. Does it make it onto the main news? No, it's it's Groundhog Day. So about 10 minutes of the news is about whether a groundhog came out of their hole or something, but not about the IPCC report. I mean, we've dumbed things down so much, it kind of scares me sometimes. But that's also our fault to some extent. We have not done a very good job of showing the importance and the excitement of what we do to the general public and to policymakers. And I put an onus on us, and I'm trying to do a better job of it myself later on in my career here. But I still have a bit of frustration with some academics, for example, who things have changed. When I was young, much younger, I cut my teeth on acid rain. And I know at that time, it was not popular for a young professor, to go on television and talk about their science. I mean, I think my PhD supervisor would have been horrified that I was doing that. I felt we had something important to say. The taxpayers had paid by and large for the research. They should know what's happening. And if you don't fill it, that information vacuum is filled very quickly. Often industries who have vested interests are going to fill that information vacuum if we don't fill it. So we have to do a much better job of doing that. And things have gotten a lot better. Universities have communications department. Before I was totally on my own. Now there's this whole, there's several people in one of the buildings on Queen's University. That's what they do. They get press releases out and they get people connecting. I think universities have realized it's certainly to their advantage to do this. But still, a lot of professors are reticent to do that. They do it they usually about 4 excuses I tend to find. The first is don't have enough time. Well, I say we're all busy. Yeah, I agree. It takes time, but it's our own best interest. Just look what's happening. It's our own best interest to make sure people realize what we're doing and appreciate why it's important. Some people say, well, what will my peers think? Well, that's kind of what I would have maybe had to worry about when I started. My first reaction is you're not doing this for what your peers think. You're doing it to tell the public and policymakers what you're doing and why it's important. So you don't care about what your peers think. Sometimes I get, well, what I do is too complicated to explain. And I just roll my eyes at that one. If you can't explain to an interested person why what you're doing is important, then you probably don't understand what you're doing anyway. So that's an issue there. And then the last one is it might get unpleasant. And I know damn well it can get unpleasant. I'm typically on the end of very bad news. And so, yeah, it can definitely be unpleasant. But that worries me. If university professors who have all various types of protection aren't getting involved, if we start self-censoring what we say, there's no hope. I mean, I think, and that's why the university research is so important. We technically, if we're telling the truth, can't or shouldn't be censored. And that's what we have to be careful about. But I see people doing that, and they're worried it might be unpleasant. It might be not even unpleasant. Well, I'm going to need a letter for another grant from this group, and I don't want to make any waves. If academics start self-censoring, I think then all is lost. So again, the importance of university and university-based research and university teaching.
Very well said. Our current top rated is just a comment to say fabulous talk. Everybody loved it. The next one, though, is so beyond kind of creating the knowledge necessary and doing the work and getting the information out there, are there other ways that we could be engaged in helping people change their behaviors or the actual response that people have to the knowledge? I know it's outside of our expertise, but.
Yeah, well, partly by example helps, but you're right. I mean, it's one thing to tell, I'm not saying any of the solutions to climate change are simple. I think we just have to show that we as citizens have power. We have power over at least 3 major things. One, we have power of our actions, and that's not easy. I'm not certainly not perfect, but but we can all decrease our carbon footprint. And I'm trying, and we're trying, but we can do it with our actions. We can do it with our wallet. We can make a decision that where we're going to spend our money or where we're going to put our pension funds or something is in something that is conducive to the environment and not against the environment. And we have a lot of power with our wallet. People will very quickly make changes when money is involved. That I have no question at all. And in a democracy, we have power of a vote. If we start telling our politicians that, in fact, this is a really serious issue, or you're not going to get reelected, they will listen to us. I think that's the problem. The environment sort of inches up, and then, it's, the economy, and that always just drives me crazy. It's like environment and education is a cost. Environment and education is not a cost. It's an investment. I mean, where did this idea come as a cost? We could talk about education. It's definitely not a cost, but let's talk about the environment. If you go to Ottawa or Toronto and you sit at the cabinet table, not that they invite me to sit at the cabinet table, but if you sit at the cabinet table, everyone sitting at a cabinet table is intimately associated with the environment portfolio. They may not know it, but they are. I mean, forestry, fisheries, tourism, health. I mean, how far do I have to go? Everything is linked to the environment. It's not a cost, it's an investment. And the environment, nature is slow to pardon our mistakes. we are making errors in our environment that are going to be very hard to fix or maybe can't be fixed. Extinction is forever. Just the fisheries document we were talking about earlier. So, this I think is something we have to do and have to get across that environment and education, to get named 2 E's, are investments. They're not costs. And the amount of money spent to fix an environmental problem, there's various estimates, 36 times, 50 times. The cheapest thing to do is not to cause a problem. I get this with climate change. Well, how much is it going to cost this climate change? That's the wrong question. It's how much is it going to cost not to deal with the question? That is the real question we should be asking.
Absolutely. Okay, and so then I guess narrowing down a little bit more to those of us who live in places where we're intimately connected with lakes, we're in the city of lakes, and really most places in the country have those kinds of interactions. Are there things that we should be doing as residents? Are there priorities we should have on our own properties, or should we be, putting pressure on folks to make better decisions in places where we're really interacting with aquatic environments?
Yeah, I think we have to do all those. I mean, if you're living on lakesfront, I think John Gunn and others have talked about this in the previous lectures, but, if you're going to start fertilizing your lawn on lakefront, that fertilizer, a lot of it's going to make its way into the lake, and you're going to start fertilizing the lake. There are things we can do, good septic systems, careful about what insecticides or whatever we use, erosion, all these things. We're all part of the solution. We've caused the problem. The lakes didn't get to this state on their own. We did it. We can reverse it, though sometimes it gets a little too late once things are really bad. So, I would talk to the professionals. There are people who spend 30, 40 years trying to figure out why this lake has a problem. You can listen to them, or you can listen to someone else who has no background, but talks loudly and waves their finger. I mean, to some extent, we have to look at the expertise. There's these, we're seeing a death of expertise, and scientific expertise is what got us to where we are today. What, negative and positive. And if we don't follow it, the situation is very bad.
Okay. You did talk a few examples of incorporating traditional knowledge, but do you think there are other places where traditional knowledge can come into that research pie you were mentioning?
Sure. Yeah. Well, I think things have really changed in that view in my career, certainly. We don't have the luxury of excluding any solid good information. And certainly people who have lived on the land, if I have a model, say I have a model that I've developed and I say this lake never had fish, and I talk to an elder at a community and says, well, my grandfather used to fish in that lake. I go, it's probably time to check that model. So if nothing else, it's an excellent form of peer review of the type of Western science we do, but it's much more than that. Many of these areas, I talk to my ornithology colleague, we do work on seabirds too. And, the indigenous peoples know where the birds are. They know where the game are because they've been following it for years. They know about ice conditions. We don't have that monitoring data. We don't have that information. So we don't, and I just want to clarify, we don't have the luxury of excluding any good information, and it is good information. So, and we're seeing a big push towards incorporating that much more than used to be. In fact, I sit on a large number of committees, as you know, with the government, and it'd be impossible. We wouldn't sit on the committee if there weren't Indigenous people on it anymore. We'd have no credence if we did that. So things have really changed a lot there in a very fast. I'm sure for many people nowhere nearly fast enough, but it's for way things normally change. It's changed so remarkably fast, at least for me. It is quite striking.
That's nice to have a good news bit. Okay, so this is another one that's interesting. We've talked about salt, I think, in every one of the talks, but with climate change and evaporation, are boreal lakes going to become more salty just because of climate without the things that people are doing?
Depends on lake. Here we're in most boreal. There are some boreal lakes that are getting salty. I should say that I've worked on some, southern Yukon, for example, right on the edge there. But by and large, road salt's definitely an issue. But by and large, the salinity changes are subtle compared to the precipitation changes in boreal forest lakes. There's other issues that override it. Technically, of course, if it got so warm and you evaporated the lake right down, it's going to increase in salinity just like everything else. But they're still pretty subtle given the amount of precipitation evaporation going on. So we haven't really seen that. We've seen it in ponds like I showed drying up slowly. And certainly there are lakes in Western Canada that are naturally salty, and they're getting saltier with drought. We were reconstructing drought frequency in places like interior British Columbia, Saskatchewan, parts of Manitoba, Alberta. They have what are called saline lakes, and they're quite. Some of these are salty, much saltier than the ocean even now. They're very closely tracking drought frequency. But for the boreal forest, it's a relative. The big thing of salt is road salt, which if you're near roads, and we're doing work on that. We're showing changes there as well with our paleo techniques.
Okay, so this is a bit of a change gear, but how do you feel about, and I'm thinking this is Canada's, but our targets for reducing greenhouse gas emissions? I mean, with the positive feedback loops and the things that you've been talking about, do we need to push?
We need to push for sure. I mean, things are a little more positive, I say, than they were with at least government initiatives, but words are cheap. All the targets, of course, are in the distance, well past the political mandate of 4 years, maximum 4 years. And I think, it is possible to get to net zero Canada. It requires a whole things happening. If there's enough political leadership and enough of buy-in by citizens, we can. I am confident we can get to net zero by 20, whatever, I think the number is 2050 or 2030. It is possible, but it's going to take some work. And we have to do it. We don't have a choice. So I think we just have to get across that it is possible to do. I don't want to end on a negative note here, and we just go from there. I think it is possible to do that.
Okay, we've got time for one more question. So sometimes even academic research, or the opinion here is that even academic research can be curtailed either by industry that's paying for it or other, incentives behind funding agencies. Do you see a solution or a change of the system that's required there?
Well, at least yes, it could be if you're funded by, especially industry, and then if you have any attachment. But you're right, it might not be a direct attachment, like the industry has to pass this before it goes to publication, which would be worrisome. It might be more indirect, like saying, well, I want another grant. So, however, we do have in Canada, at least, a very important funding of the Natural Science and Engineering Research Council, which is called the Discovery Grants, which are unfeathered, and they're free. They get tremendous bang for the buck, I would say, because you are not bound by industry. You're not bound by getting an answer that is convenient. You're bound by getting the answer that is right. And I think we just have to preserve that fundamental aspect of research. And again, that's another aspect of the importance of university research. A lot of it is not attached to you need this type of answer or that type of answer. So we'll always have some of that. But I think the fact that when you're in university, that is where you do that kind of work. I think it's much more difficult doing that if you're an industrial scientist. And it's often, I think, difficult even a government scientist, because the political whims of the government in power is to some extent the employer. And, we've seen that in various governments in Canada and certainly elsewhere, not just in Canada.
Well, I thank you so much. And I wish we could have gotten to all the questions. Thanks everybody for submitting those. And I think we've got 2 minutes for Richard to wrap it up for us here.
Thanks, Bree. So this brings us to the end of our Troubled Water webinar series. I'd like to thank all of the people who contributed to this event, our partners, the Ballet Living with Lakes Center and Federation of Ontario Cottagers Associations, the audience for their questions, and those working behind the scenes tonight. Michelle Levin from FOCA, flawlessly managing the Zoom webinar system. Nicholas Smith, Richard Denton, and John Lindsay from GSWA working on technical support. Bree Edwards from Ballet Living with Lakes, introducing the speakers and managing the Q&A sessions. And most importantly, our speaker for this evening, Dr. John Small. John, I was really disappointed to see how much sediment had gathered since the Maple Leafs last won the cup. But your presentation was a powerful description of the factors that can be addressed by paleolimnology and it demonstrated the climate-driven shifts in the biological community's Arctic lakes, the increasing prevalence of the serious ocean flooding events, and provided data that really challenges our previous understanding of the major causes of algal blooms. Climate change is indeed the new threat multiplier. We've been encouraged by the number of people who have attended this webinar series and the positive feedback it has received. Ironically, it was COVID-19 that changed a one-night event in Sudbury into a virtual series of webinars that have allowed many more people to participate in. Each of our 5 presenters in the series has shown how data from rigorous research over time contributes to both our understanding of the changes occurring in our environment and informs the responses we may make. The importance of gathering good data and basing decisions on the best evidence can be easily illustrated by the differing responses by Canada and the US to the COVID-19 pandemic. In Canada, most governmental decisions have been evidence-based, whereas many US decisions have been based on partisan politics, self-interest, and ideology. As of today, the calculated COVID death rate in Canada stands at 5.86 per 1,000 people. And in the US, it is 15.66 per 1,000 people, a US death rate nearly 3 times the rate in Canada. Like COVID-19 pandemic, climate change will create serious challenges in the coming years. And our ability to successfully address these challenges will be determined by how well we understand the issues, by how well informed we are by research, and by how well we align our responses with the evidence. If we don't support the excellent research programs exemplified by the webinar presenters, we will lack the information necessary to make appropriate decisions. If there ever was a time to strengthen our research capabilities in preparation for the future, now is that time. We welcome any feedback you can provide about this presentation and the webinar series when you leave, and our link to the survey. Stay safe by following the COVID regulations in your area, and good night.